Hello, this is a small introduction to Haskell. For this introduction I will use on the right my editor and on the left an interactive shell which is called GHCA. And I already wrote a bit of boilerplate in my editor, but you really don't need to focus on that. I will discuss binary trees. Obviously this kind of talk will be better with slides instead of a live session, but I'm too lazy to write slides for now. It was just a proof of concept. So a binary tree is something really known in computer science. It's a tree representation which can store value, and usually you have something which is called a node, which contains a value and two sub-trees, the left subtree and the right subtree. And each subtree can be a node, which can contain a left and a right subtree, or it can be a leaf, which is obviously the end of the tree. For this talk, we will not focus on ordered or balanced binary tree. We just focus on binary trees, so it can be any kind of tree with any kind of value and no relationship with the value between them. For the value. So, how do we represent that kind of type in Haskell? We write data tree t. This means that we are creating a type which is called tree and which is polymorphic and can store any t. This is interesting because with that we will be able to store strings in the tree, integer in the tree, chicken in the tree, anything. So now we will list all the cases. So our tree can be a leaf, or a tree can be a node. And a node stores three values: left subtree, the current value, which is of t, and a right subtree. Okay. So now we create the type tree. We list all the possible cases of this type, and this magically create also the function which will help us to create an effective tree. So I will just reload my file and create a tree. So my first tree contains only a leaf. It's an empty tree. Okay, I can also create another tree which contains well, I will create the tree which is depicted here. So first it's a node which contains a left subtree, which is also a node, which left subtree is a leaf. The value is 5, and the right subtree is a leaf. Okay, and this is the left subtree of this node. The current value is 12, and the right subtree is a leaf. So I have created another tree. Okay, what can I do with trees now? I can write function on trees. So, for example, I will compute the sum of the tree. So I would call the function sumTree. And in Haskell, we are doing case analysis in most functions. So the sum of a leaf tree, of an empty tree, is 0. Okay, and now the sum of a node, which contains a left subtree, a value, and a right subtree. Is okay. I will just stop a bit on this pattern. This is called a pattern, and it helps to unpack value. In most languages like Python or stuff like that, you may be used to pattern like a, b equal 1, 2, and a is no 1 and b is no 2. Okay. In Haskell, this thing works on any type, and if you write, for example, node sub a v sub b it equal node leaf 12 leaf, sub a will be okay. I cannot show that there is no way to show what it is, but sub a is a leaf, v is 12, and sub b is also a leaf. So I'm using this function and this syntax to get my left subtree, my value, and my right subtree. So now it's a recursive function, and if I want to compute the sum of everything, the sum is the current value plus the sum of the left subtree plus the sum of the right subtree. excuse me, write subtree. Oh well, actually this error was interesting because Haskell is a statically typed language. It will show me errors. I mean syntax error, okay, but it's also statically typed, and you cannot do weird kind of computation. I mean, I cannot add a string to I cannot add a string to something which was obviously a sum on an integer. So this is interesting because it's statically typed, so it's statically checked, so check during the compilation time, so before execution, compared to Python or Ruby or this language where the check are done at runtime. But on the other hand, there is no boilerplate. You don't need to write type annotation anywhere because it's inferred. The type are inferred. So well, you get the best of both worlds. So okay, it's done. I write in my sum tree function, and so if I reload my shell, I can compute the sum tree on my tree. So this is still my tree, and the sum of this tree is 17. So it's all right. It's what I wanted, so it's appeared to work well. Okay, I can write any other function. Okay, for example, I can write a function which assumes that the tree is ordered, and that anything on the left tree is slower than anything than the current value, and anything on the right tree is bigger than the current value. And with that, I can write a minimum of maximum function. So minimum tree of a leaf. Minimum tree of a leaf. Okay, this is a special case. I don't want to. Okay, minimum tree of a node with. Yeah, you know what? I will not write that one for now. Okay. And no, my video is just stupid, and I just lost my focus, but it's alright. I wanted to discuss how types can help you, and how types can remove boilerplate. So what if I want to print my tree? Okay, I can write a complex function, a print tree, which print a leaf, and print a node. Node left. Okay, this is boring. I don't want to write that because I can derive it automatically for me. So by writing deriving show, I ask the compiler to write a generic function with a generic algorithm which works for most types. It will derive me a function to display my type. So I can show my type t, my tree, and I get a string representation of my tree, which is really useful for debugging. Okay, but I can also derive equality between tree. So t equal t, obviously, and if I create another t and t equal a leaf, it's false, obviously. So I did not write any code, and it derived, the compiler derived the equality for me. I can also derive ordering, but for a tree it's a bit weird to discuss about what is the ordering of a tree relative to another tree, so I will not, I can use that it works, but well, is this tree lower or bigger than the leaf? Okay, the automatically deriving an ordering function is not that interesting. Okay, I can derive a generic. I don't care about it for now, but I will care for the next two. I can derive hashable, which means that I can hash my tree. Hash tree t. Okay, this is really great because I can have hashing for free. Okay, I can derive serialize. Okay, which gives me serialization for free. Okay, trust me, but this can be decoded, and I will get my tree back. So for example, decode t will give me decode the encode t. I need a type annotation because decode doesn't know what type you want to decode, because it's not encoded in the string. And it's a tree of int. Well, it's a tree of integer, sorry. There is a difference between int and integer because int are word-sized integer, and integer are integer with infinite precision. So, well, okay. I encoded and decoded my tree. Okay, I can derive. Oh, there is some really nice stuff I can derive. For example, functor. Functor is just a generalization of map. Map, you know, like in MapReduce or in programming language. If you use Python, map exists. If you use Ruby, I think that there is a map function, but it's not called map, so I don't remember. Excuse me. Okay, but well, map 2 times. Actually, it's called fmap for some reason. Actually, functor map. Okay, map times 2 on the list from 1 to 10 give us the list from 2 to 20 by step increment of 2. Okay, but I can also do that on a tree for free. Okay, so well, I recreate my t, and I'm doing times 2 on my tree, excuse me. Up I get the node which value 5 is now 10, the node with value 12 is not 24. It's marvelous. Okay, I can also write foldable. Foldable is a way to write a fold on an expression. A fold is something which just put a binary function between any terms of an expression. For example, fold plus 0. Okay, this will write 0 plus 1 plus 2 plus 3 plus 4 and so on. Okay, and give us the sum of from 1 to 10. Okay, and now that I have derived foldable, I can do the same with my tree. So fold plus 0t gives us 17. Okay, like the sum tree function. Actually, it is the sum function. If I do sum tree, okay, 17, it's all right. And this sum tree comes for free with foldable. So I can remove my sum tree function. Yes. Okay, and I can also do minimum, the t, maximum, the t, length, the t, and so on. Everything's come for free with the foldable function. Obviously, there is some cases where you want to override this default behavior, because if you have a binary tree, usually it's an already ordered binary tree where the left subtree is every value in the left subtree are smaller than the node, and every value in the right subtree are bigger than the tree root. So and in this case, it's easier to there is an efficient algorithm to find the minimum and the maximum, and so on. So you can write specific version of the functor, foldable, hashable, and so on algorithm. But for most cases, the default are smart and usually what you want to do. So well, on this case, the only one I will overwrite myself is the foldable one, because all the other ones are usually correct and generic. Now I will use the few minutes I have to show you that the tree is obviously polymorphic, so I can create a tree with a string inside them. So hello and world. Okay, so this is my tree, and as I said, I can map length on my tree and get a tree with the length of the two string. I can oh, there is a really nice instance I forgot to tell you. This is import test.QuickCheck. Okay, that one is really great. I will create the arbitrary instance. Use the arbitrary instance. Okay, arbitrary is. Oh, excuse me. I'm just wondering. Okay, we'll test if it works. So, if I'm doing library in Haskell which is called QuickCheck, in Python there is something similar which is called hypothesis, and I don't know for Ruby and any other languages, but the idea is that you can write test property testing. So the idea is to write a function in which you don't know the input, but you write a property, whatever the input are, you have to match a property. So and for this you need some way to generate arbitrary value, and by deriving arbitrary you'll get that. So if I'm using the generate function, I need to reload my tree, and if I'm using the generate function, and for which I don't remember, okay, which is arbitrary tree. Okay, I will get a tree. No, because there is no generic code for arbitrary, and I was not aware of that. So I will write it in a few seconds. So, okay. So the instance, okay, for a tree t, as long as arbitrary, as t is arbitrary, is arbitrary equal, will choose between a leaf or a node, and I need to, let's go without any harness. So I need to choose between a leaf or a node. Okay, don't focus too much on what I'm writing. Up. Okay. Okay, and this should work. No. I'll choose it's one off. Okay. One off. Oh, you meant one off. Okay, let's go. And I can generate a tree. Okay, I can arbitrarily generate a tree. I take a leaf, with a leaf, another leaf, still another leaf. Oh yeah, this is a big tree. So I'll try to get my tree. Okay, this tree is interesting. I can compute the sum of the tree, obviously. Oh, I removed the foldable instance, obviously, because I said that I didn't want them. Okay, and the time is off. Just to say a bit about this function, I just said that I wanted to write the function for arbitrary for tree, and there is different function, and using in the arbitrary, you can use in the arbitrary library. But this one, they said, okay, a tree is one of, it's a leaf or a node. Okay, the pure function here is something which you will learn if you do a bit more Haskell later. Okay, and a node, I'm using the node constructor, which takes a tree, another value t, another tree t, and and I will, the left subtree will be generated arbitrary with arbitrary. The value will be generated with arbitrary, and the right subtree will be generated with arbitrary. And there is a chaining. Normally we can write a node like node A, B, C, but because of some reason you will learn later, we'll use this gimmick here, but except from those gimmicks which are really standard Haskell later. I mean, this can be difficult to read at the first time, but later it will become as easier to read as reading something like this in C, for example. In C, you can read tab crochet crochet. This is French for bracket. Excuse me. Equal tab other tab gr++. Okay. This is complicated for someone who doesn't know what is the plus sign, what are the brackets, and what is the semicolon. I mean, and once you've done a bit of C, this line becomes really easy to read. But for someone who'd never done C, it's complicated to read. This is the same thing for this line in Haskell. If you've never done any Haskell, those two signs are complicated, and the per one is complicated too. But once you've done Haskell, this becomes really generic and really useful. So, okay, time is over. I said a lot of crap. It was just a test. So, bye-bye, and thanks for listening. My really nice French accent. Bye-bye.